Okay, cool. This is my cool build-up slide. I will say hi in 2 slides, so give me this chance to tell this little story. So maybe you have ever seen or written code like this, and here we have a HTML form, for example, and we have an email password, confirm password field, and all you want to really do is make the submit button enabled and disabled depending on the validity of your form. And you can imagine that if this form gets more complex, your code might get more complex as well. Problems with this approach: you need manual coordination between these functions. You have repeated calls on update submit button, hard to track what's affect what, and easy to forget your UI update calls. And maybe you've wondered, is there a better way to model this? Welcome to Reactive Programming with Hexe and ThinkState. My name is Michael Engel. I work for InnoGames for like 10 years or so now. And with Hexe, I work for like 3-ish years. And I'm a front-end developer in Forge of Empires. So let's get starting. And this is how it will go down today. So first, I want to introduce you to reactive programming in general. Then we're going to say hello to ThinkState a little. And then I want to do a little more of an advanced topic, which is comparators. This is the only advanced topic I was allowed in this 40 minutes, because otherwise it would like explode the talk. Small wrap up and resources. Let's get started. Introduction to reactive programming. Let's start with something you all know and are very familiar with, which is an array. And an array, it sits there tightly in your memory and does nothing very special. In this case, it holds 3 values. And usually what we do with arrays is something like this. We do a for loop. And the for loop, when we think about it, it basically takes, at our own convenience, one value out of memory from this array, and then does some computational intensive operation on it, like in this case, trace it. And then we are ready to do the next value. We take the next value. And this is what I want to call the pull method. We pull the next value when we are feeling ready for it, and then we do some computation on it, right? It's easy as it is. But what if we now start to introduce time to our array? What if we think instead of user clicks, of stuff that is not there yet and that will happen in the future? So we don't know yet all the values that are in this array yet. So values will arrive later, not all at once. And obviously our little pulling and looping does not work for these future values. That does not really do. We don't know how long the array is and whatnot. So what can we do? And you guessed it, because I said pull 3 times now. We introduce something that we call the push method. So we turn this whole thing on its head, and we give the responsibility for these values to some source outside of our control, which we call a sender or data source. And then we just wait for stuff and react to it. And this basically is already like the gist of reactive, but you are wondering maybe what can be pushed and what do we need to tell or get told from the source. So first, we need a new value. We can define a function that is maybe called onNext, and we can pass a value into it here. And this is our next piece of data. And we obviously also need to communicate something went wrong, so we define onError and give it an error state. And then lastly, we give it an onComplete state. So then we should have all the information that we need to actually act on what's coming in. So let's summarize this really quickly. So a source can signal us 1 or 0 or more of these onNext calls, and then it will be followed by either the onError or onComplete message. This push pattern has a name, and it's the core idea behind all of the reactive programming, and it is usually represented by the observable concept. The observable idea is something you can subscribe to. And when you subscribe, you give these 3 functions to the thing you subscribe to. And what happens is, we will see in a second. So in Hex, it could look like this. We have an interface observable, and we define subscribe, and we give it our 3 functions as simple callbacks. Let's quickly, because this is kind of the key idea here, let's quickly recap these little things. We have the arrays with the pulling, we have the events over time that we introduce, we have pushing that needs these 3 signals of on next, on error complete, and we have this observable structure. And reactive programming, in its core, it's all about reacting to streams of data and events. And let's now go more and use our observable here a little bit. So this is the simplest way you can use an observable. We just defined in our head. Basically, we define the thing, and then we give it our 3 functions. In this case, 3 times trace. And what will happen if we subscribe and run this code? Obviously, it will give us the output that we might expect, like 10, 20, 30, and so on. And this is already very similar to what we did with the for loop in the pull worlds. But now we turned all the responsibility on its head, and now we are just reacting to stuff. Let's go back to our email form. How could that look like? So instead of creating pulling values from a password field and then running a check password calculation on that field, we now subscribe to the password field and react to all the new values it's getting. This concept is the foundation of all the reactivity that you need to know, and it's basically where you get started. But obviously we have some questions. The first question you are having is, what if the source is too fast? Obviously. And so imagine a stream of mouse movements or something that is really fast, and you are very slow in your computational expensive operation. You're drawing to the screen. So I want to give you the terminology from literature here, which is because this behavior is called back pressure. And in the future slides, we will also talk about back pressure. So I introduce the word here. Back pressure is a source that produces faster values than the subscriber can consume, and there's no unified answer to back pressure. Different reactive libraries offer ways to manage this. Next question you have in your mind is probably, what if multiple people subscribe to one source? Because now they can, and they will. And if we think about it, what happens with the data that you are getting here? Basically, the question here is, will the source start with a history of all the data for each subscriber, or will you just connect to the live values that you're getting? It's basically, you can think of this, and the literature defines this as hot versus cold observables. So cold observables is basically a YouTube video. Yeah, you can like and subscribe and watch the content at your own speed. And see also the complete history. And a hot observable is like a live stream. A Twitch stream, for example, which you're watching right now. This is important also, another thing from literature, and in the later slides you will become more clear why I explain these things now. But lastly, the third question you all have in mind is, what else can we now do with the observables, since we just defined them, right? So the reactive libraries usually give you building blocks for and deal with all the messy stuff, like concurrency and disposal of things, and I don't want to go into details about these kind of things right now. The really fun things comes with operators. So now we have an observable type, and now we can do fun things with it. And operators is now the power that the all reactive programming and observable thing gives you. And the idea here is you don't change the original stream, you produce derived streams by using operators from it. How this might look like, for example, like this. We have an observable that creates numbers, and 1, 2, 3, 4, 5, and so on. And then we create a new observable by mapping the first observable, taking its input value and creating the double of the number. And this will give us actually then now 2 observables which we can choose to subscribe from. Same thing, for example, with filter. In this case, the filter function drops half of the values from the original observable, which can be valid back pressure mitigation strategy. You just learned the term, right? And you can drop values here. But you can also use operators, for example, to merge data. For example, here we have the merge observable operator, and it will give us one observable which reacts to 2 input observables. So popular operators in different frameworks look like this, more or less. They might be depending on your framework. For example, rx.net will rely heavily on C#'s link, and it might look different in your mileage may vary. Where I want to get to with these things is, and I want to give you this picture in your head, which is of a stream of water pipes. So you're building a network of water pipes in your application, and the water is obviously the data that is on the top, and it flows down in your network through all these things, through all these observables, until it reaches your UI and you react to things and you bind to your observables. And these operators are basically changing the pipe size and transforming your pipes and splitting them and merging and whatnot. And this is, it might sound stupid now, but the idea here is that we will see in 2 slides. Give me this. An example first. Here's our email stream, password stream, and isValid stream. And in real life now, since we changed them to observable streams instead of having just variables, what we see now is that they change over time. This is exactly what we wanted. So the user types stuff, and the stuff, the observable will react. So they represent a stream of facts that happen over time, and this is mostly read-only. So you change your behavior in your in your application from having state that is mutable to having observables where you react, which are by default immutable, read-only. And this is also where this water pipe analogy makes more sense, because you have the pipes and you don't touch the water, you don't change the data, so you only deal with the pipe system, with the piping. It's still a bit of a stretch, right? But it has a state management implication. So if streams are read-only, then how do you change your state then, right? So you can't just flip the variables back and forth. And you have to think of state updates as new facts, so as new water that needs to flow in your system. And the only way we can do it is at the top of your water pipe system, of your network. So the whole observable reactivity programming idea fosters unidirectional flow, unidirectional data flow in your application. And when you use observables, you see that your application will start to transform into something where data just flows from one end to the other and only derive new knowledge by computing it from existing. So here's an example. You have user actions and events, and they are somehow dispatched in your whatnot. And at some point, it enters your state system. And from here on, they become water in your pipes. And then you have all these operators on them. They transform and And at some point, your UI elements bind to them. And this basically then exits your pipe system again, and your UI can react to the changes presented. So some key takeaways for the general introduction to reactive programming. So we had the arrays with the pull thingy first, and then we introduced observables, which are basically the push system. We talked about that we need on next, on error, on complete to make the picture complete for the observable. We talked about back pressure. I also introduced the terminology hot versus cold observable to you. And then talked about the operators and the water pipes. And this leads to a unidirectional data flow and a single source of truth. And that, ladies and gentlemen, and everybody else, is already the introduction to general reactivity. And I want to continue by talking about thing state. So now we learned about these core ideas about reactive programming. Now how does it look in a real hex library, right? This is what we really want to hear to see. First, credits, hex Tink or Tink State was developed by URI as part of the Tinkerbell collection of libraries. There's a huge stuff. There's lots of wonderful, awesome stuff in there. You can go check it out. It's really a lot. And this is Tink State is only one part of the whole package. And in this occasion, I want to also shout out Dan here, who ported Tink State to C#. And I gave you the URL here, which you can also check out and use the whole thingy also in C# if you like. So let's get started. How do we get started now before we drop everything? We do it like we always do it. We hex lib this thing, we minus lib this thing somewhere, and then we import stuff. And then we are going to use it. But first, Tink State is a library for reactive state management, and it gives us a couple of classes and things we will look at, mostly observable class we just learned about, values you can subscribe to, but it also gives us a state class. You can think of that like in the same way like an observable, but it has a writable value, so it has a clearer distinction between writing and the read-only part of things. It has some reactive collections with observable array and observable map and other goodies. It has tools for async operations, and it has some advanced features like comparators and guards. But how is it used? It's used like this. You create a counter, new state, give it a default value, and then you bind, which is the Tink State terminology for subscribe. You bind to that value, to that new state, and then give it your callback and change the value as you like, and this will produce an output like you would expect it from this. Observable, so the observable class in Tink State works similar. So we create here in this example, we create two states. And we create something where we look into in a few slides more. This is the magic observable auto. And we just use the values of the two states we just created and then bind to this newly created observable. So we basically build a small pipe network here. And then when we trace, we will get the sum of the values, which are in state 1 and 2. And the magic here is as soon as we change one of the states, the sum will automatically update. So it will always be the correct sum of the two state data fields. So one thing to note, what makes Tink State different from other reactive libraries, and my introduction was a bit more broader towards other reactive libraries. I talked about all these operators, and Tink State has all these operators as well. They are there and you can use them. However, its core innovation is observable.auto. And observable auto gives you all the magic that you need in your life. It basically gives you the automatic dependency traction. You don't need too much about manage your subscriptions too much, and it also fosters the efficient batching part of Tink. How does it work? Basically like this. You just create observable auto and then use your states or your other observables with the dot value thing, and Tink State will magically look into this code and pick your observables and starts tracking them right away. So you don't need to deal with all the tracking part of this. And if any dependency changes, your binding is rerun and your subscribers are notified. Here we go back to our email example, and we now have all the knowledge already to create our email example with Tink State by using, instead of plain variables, we use new states for the email password and confirm password. And then we already start to derive knowledge from these three states. Like is valid email, we create an auto observable, blah, blah, blah. Is valid password, same thing. And at the end, we have the can submit auto observable, which derives all this validity to one true or false value. Really cool already. One more thing to note. In think state, there's a difference between the hot and cold thing I talked to you about a couple of slides ago. Because think state does not have this cold observability that many frameworks outside of think have, where you get the full history of the data stream. In think state, all the observables are hot by default. There is an internally, they are named cold and hot, but that basically just refers to if they have subscribers or not. So be aware of that a little bit, and then you're safe. And when you look into literature and other frameworks, you know the difference. Think state also features batch updates. What that means is basically if you do updates of state during a time frame, then they will be batched into one update. Here in this example, there are updates to first name and last name, and it will only trigger your binding once because probably it happens in the same time segment, the same second, in the same frame, whatnot. So there's a scheduler behind the scenes running and batching updates. This is an efficient performance optimization that is built in. There is a possibility to manipulate the scheduler, but I don't have time to show you today. It will be part of a future talk. Here we have an example of think state with operators, where I just have a state and then use a couple of operators together, chain them nicely, and then process the result in a binding. You can totally do this. If this is your thing, go ahead and use the operators. But there's also observable auto, and observable auto, like in this example, this is just makes code a little bit nicer because you can maybe read the bottom part of the thing a bit better or know what's going on instead of having all this top part where you have to deal with all the operators. So observable auto is the way to go, and in Forge we use observable auto like 99.99% of the time and mostly no operators on observables because it's so nice. Here's the second part of the email example. So now we are really complete, and we can bind to these observables we created 3 slides before and update our UI, set class names on fields or however you update UI, and then you can bind to them, and then your password form will be really cool and reactive, and every time one value change, all the states will, all the bindings will fire, and all the states will update, and everything will be always in sync and in a good shape. Which also goes a bit in the direction of how does imperative versus declarative code look like. So in the old example, in the first slide, we saw a lot of imperative. So imperative means I tell the button how it should update. And with think state, you are going to write more declarative code, which is basically just giving the rules, and how things is happening is done by think, and the framework will do it for you. So you don't need to wire up all this stuff again, which is really nice and can give you a lot of cool benefits and make your code more readable, understandable, maintainable, And this is already the introduction. So a key takeaway for think state is a lot of automatic is happening. You just declare how values are computed. Think state does track your dependency. If you do the observable auto thingy, it has efficient batched updates. And it also focuses on the declarative side of things. So you don't need to wire up too many listeners and tell the system the 100th times how a button should be enabled and disabled. And now you can already go drop everything and go explore think state, because the basics are there. Yeah, you learned about reactive programming. You're basically ready to venture into this world, read literature, and also explore think state. It's really easy to use. It has little dependencies. You can use it in your project right now. Drop everything else, and will be enlightened. But for sake of giving more information, I will quickly dip into comparators, which is also a feature of think state and a bit more advanced. You probably don't need it 80% of time, but let's go. What is a comparator? A comparator is a function that takes two values of something and returns true if the values should be considered equal and false if they are different. It's like this. Equal, true, not equal, false. I have to say it to myself, equal, true. You can use comparators or functions like this in basically in three places in Think. First, as a second parameter to the bind function, then a second parameter in the auto function, but then, and this is that makes the whole thing interesting, as a second parameter to the state. And comparators, how do they work? Well, like you would guessed it, they compare old value versus new value, and then, like I said, if it returns true, then they are equal, no notifications. If they returns false, then observers will be notified. The default behavior of comparators is basically with the equals equals operator. So if you give nothing, then there will be used. So it will be totally easy and cool for integers, like in this example. So you give two values, they're different, and the binding will fire. It might get more interesting if you have more complex objects and classes and things. So here is the real use case for comparators. Yeah, and like I said, you can put them in state and you can put them in binding, but remember the state is usually the stuff that happens on top of your pipe system, and the bindings are stuff that happens at the very bottom of the pipe system. So it builds a hierarchy where comparators are used. And the hierarchy resolution is basically like this. So first you change a value on a state, then the state comparator will be asked, hey, are these values equal or not? True, false. And only if the state comparator says false, values are not equal, then the whole thing the binding will trigger, and the binding comparator will then be asked, hey, should I process the whole thing? And only if this guy also says false, then your binding will fire. So hierarchy, two things. You can think of the state comparator as a gate. If it considers the value is equal, no invalidation occurs, no value will be set, and obviously no bindings will be triggered at all. They won't even be notified about it. And then the binding comparator you can use as a filter. So here in this example, it's a bit more, but you get the idea. You use a comparator which always says false in the state, so it will always pass down to the bindings, no matter what we put in the value. And then we have one binding which also gets this always false operator, so this will always fire no matter what we set. And the second binding will get the comparator which is always return true, and it will only fire once when we set the initial value. So then we set two values, and then it will do what we expect from it, hopefully. When binding comparators are used, so yeah, this slide is basically you can do that, and then if you not do it on the state, for example, and do it in the binding, then the state comparator will, as a gate, will use the equals equals per default. This is what this slide want to say it. You can compose comparators via and or. So you have, in this case, you have a person with a name and an age. You have a name comparator for the name field and an age comparator for the age field. And the both comparator now says name and age must be equal, and the or comparator said either one. Right? Just makes total sense to have that, but it gives you a new comparator and you can plug in any as you like. Examples. So this one we just saw as in the never equal operator will always fire. It might sound stupid to have in your tool belt, but think of unit tests, think of mocking scenarios, think of you want to screw your coworkers. You use this one. And the same goes for the equals, always equals comparator. If you put this one, then nothing will be notified whatsoever. So you can turn off your pipe network with this thing on the top, or just use filtering in some binding somewhere. So here's our email example again, and now we are dealing with more complex form state instead of just having straight variables like we have this thing. And then we can compare a bit more in depth instead of the equals comparator, which will only like give the reference equality. For example, the newsletter field, it does not matter if the user clicks it on or off in our form, because the form will not lose validity if the user unsubscribes from our newsletter. So we ignore this in our comparator. So we can still compare and but ignore certain things. The next example is more interesting because now we can do more interesting stuff with comparators. Now we can use, in the first thing, we trim the email field, for example, in the comparator already. So it will only compare trimmed values to each other, which then makes sense to like ignore the white spaces also ever. So it could be a really cool optimization for when values change. Or the second example where we only, where we basically have a floating point number and we only want significant number changes to trigger our bindings or state or update value. This could also be an interesting back pressure mitigation technique. For example, if you have a lot of floating values in your game engine that are very similar to each other and you only want to have significant changes to pass down your pipe network. So you can use this one. Or you have, for example, an expensive call to your backend server for check for email availability, and you want to make sure that the user does not submit the same email twice or just meaningless information, so you don't want to bother the server too much. You can use a comparator and some checks to only activate your side effects when it's actually meaningful. So that was already everything I have today for comparators. And I think, yeah, it's good in time. Well in time. Yeah. Let's quickly wrap up things and give you some resources. So we just learned about the core reactive programming concepts. We talked about the fundamental shift from pull to push, from this static thing to streams, and thinking about values over time and changes. And we also talked a bit about imperative and declarative, from how to do it to actually what should happen. And we talked about observables and these three functions to make them complete. We talked about hot and cold observables, and we saw back pressure and also had some back pressure mitigation things going on. And then we looked into operators. We then saw the read-only observables, the immutable streams, and we had a dip into this unidirectional data flow. And you will see this data flow everywhere when you look into frameworks. Nowadays, it's basically what people do. And most modern frameworks also have some way of observability or reactivity to them. So all these principles are very much set into the frameworks that are out there. And you can go forth and explore these now with a little bit more background knowledge. Think States is a Hex reactive solution, which is really cool software. You can already use it now in your projects. And it has this cool observable auto feature. It has efficient bashing and very zero boilerplate, just write functions. And this Think State handles all the wiring for you. It just works. Then we quickly looked into these cool comparators, and now you have maybe some ideas to how to use them, as a state acts as a gate and the binding acts as a filter. And stuff I did not tell you because I was limited in this talk. But I have more stuff to come. Think State actually has some more tricks up its sleeve. And I did not tell you and talk to you about the observable lifecycle management. There is something to do with callback links and disposal and cleans up and blah. There are more data structures to discover, like progress and observable date. We did not look into the tools the observable class actually has. We did not talk about guards, which can be used for value sanitation as well, like we saw with the comparators. They have a little bit of overlapping use. And we did not talk about schedulers, batching, and update control. So you have actually some control about when things fire and why and how and what. We did not talk about unit tests at all, how to test these things, these beasts, and we did not go in depth about the observable array and observable map. And there are other concepts that also deal with future values like signals, promises, and futures, and we could maybe think about how we can combine these things together and make them useful. I did not talk about this as well. And also some more advanced debouncing strategies. And these are all topics you can go and discover. I will tell you in the next slide maybe where we can do this together a little bit. So this slide is basically when to use reactive programming. I would say go and use it now for everything and stop using all the other stuff. It will transform the way you think about data state and the flow of data through your application. You can also really successfully use it in an existing application, which is what we do in Forge. So we have this old game, which is 10 years old, has a architecture that is equally old when no reactivity was around, and we started to use it recently very much with huge success. Cleaner code, less bugs, more reactive UI, really cool things that happen to your application when you use it. It's also cool for games. It just rocks, just rocks. So what we talked about the reactive mindset, like just also talked about it. Everything is everything is a stream of values over time. You compose stream with operators, you react to changes, you don't poll for them, and you have the declarative approach. Some resources. So first of all, read stuff from RX if you are interested. Also, Dan has some documentation about his Think State Sharp library online, which is really cool. The documentation from Think itself, it's a little short. So this is why, when also preparing this presentation, I discovered that it's a bit too short maybe for most. So I started a Learn Think Stack repository on my GitHub, where yeah, you have not seen it yet, but it exists now, and I want to collect all the things that we can learn from things. And I already uploaded some documentation to it, and it will be obviously that when I teach or talk about these things in here at InnoGames internally, I will maybe complete the thing and update and release more talk slides and documentation about it. So this is my plan for future. I hope it will work out. Yeah.
What can we do to motivate you?
So first, let's finish the talk, and yeah, maybe you have some questions about reactive programming, concepts about think state, implementation details, or anything related to the talk.
I love that tagline. Making your code react to change so you don't have to.
This is how we roll. Any questions? Thank you.
So there was a term that came up a few times, and it's probably something you're very used to, but I don't know what it means. What's the bouncing exactly?
Yeah. So basically, also a back pressure mitigation technology. So basically, you have a lot of values coming in, and you can think of, for example, when you have a set of values and you need to decide which one to drop. So do you drop the first one? It might be important. Do you drop the last one? It might be also important. Do you drop the stuff in the middle? Do you drop every second one? How do you debounce it off your chest, off your wall? Right?
Yeah. Is it like just how do you make it someone else's problem, basically?
Yeah, you can make it someone else's problem. This is also valid technique. So when your server sends you stuff and you do computational expensive operations and it's too slow, too fast, then you can tell the server by calling a method, say, hey, please slow down. I can't catch up. Right?
That sounds very healthy.
That's no. Oh. More questions or mic drops? If not, then I drop the mic and say thank you very much again.
We didn't actually have any questions in chat. I think there was something about Minecraft, but I don't think that was serious.
I'm not in Minecraft, sorry. They are already going and checking out Ting State.
I think.
Or X5.
We have a comment here.
Yeah. I think the question was redstone hex target when, basically. But yeah, I don't have a question, just a quick comment. As somebody who's also been using Tink for a while now in Forge, I've never really seen... So I knew about comparators, but haven't really seen how I could apply them, basically, in our code. But you provided some really great examples. And now I think I have a much better idea of how to do that.
Yeah.
And let's use more in Forge, I would say.
Let's use more in Forge, yeah. That was
Cool. Thanks for the talk,
Thank you.
Michael.
Yeah, it's like I don't even know programming, and even I think this is cool. Like, this sounds very like programming went to therapy finally.